In the last section, I pointed out that practical considerations tend to constrain the overall form of the physical architecture of a complex control system. So, in an electronic system, how does this show up? As we discussed earlier, a personal computer performs lots of applications. These applications access the resources of the computer via the operating system. And the resources look like this: printed circuit assemblies and integrated circuits. The resources are organized into a particular memory processor architecture. And as we'll touch on later, the presence of this particular architecture is driven by those practical considerations we discussed in the last section. Now, how essential is this architecture? Well, we don't see electronic systems with a different architecture very often. But in the past, special purpose systems were designed with different architectures. For example, the so-called analog computers. Analog computers were optimized to perform one type of task very effectively. But as I'll develop a little later, the more features that have to be supported by a given set of resources, the more strongly the physical architecture will be constrained into this memory processor form. In other words, this architecture isn't actually a rigorous prescription. You could certainly create a special purpose architecture if it only had to perform, say, just one specialized function. But as soon as you need to perform lots of different kinds of features, you'll tend to be forced into using this memory processor form to avoid the need for excessive amounts of resources. And we're going to find a similar situation for brains. I'm not going to go into details for electronic systems, but this rather complex diagram summarizes a lot of what we'll be discussing next. How, for a complex learning system, the practical requirements along the top in red tend to result in some specific constraints on the way the physical resources of the system are organized. But again, this architectural organization isn't a rigorous prescription. It's a limit that will exist as the ratio of the number of features to be learned to the physical information handling resources increases. But on the other hand, given the huge decrease in the cost of transistors in the last few decades, natural selection quite likely exerts even more pressure on brain architectures than the pressures that exist on computers. This is a somewhat more detailed list of the constraints that I was illustrating conceptually in that earlier diagram. If the number of behaviors is large relative to resources, the resources that detect conditions within sensory input, say, and other information will tend to be organized in a modular hierarchy. The resources that select behavior will also be organized in a hierarchy. There'll be a number of resource management subsystems, and there'll be a number of architectural features reflecting necessary compromises between resource requirements and behavioral effectiveness. But a key result is that we'll find as we go through the implications of the practical requirements is that they force the existence of common information processing paradigms throughout the learning system, analogous with, but qualitatively different from the instructions and data in systems designed under external intellectual control. And these common information models, ultimately driven by natural selection, make it possible to understand the brain. So now I'm going to go through how those constraints can be derived from the practical requirements.